Example 7.11 is on page 258 and 259 in your book. Standing with slightly elevated heel. It says this: suppose you stand on your toes with your heel slightly off the ground. In order to do this, the larger of the two lower leg bones, the tibia, exerts a force on the ankle joint where it contacts the foot. The Achilles tendon simultaneously exerts a force on the heel, pulling up on it in order for the foot to be in static equilibrium. What is the magnitude of the force that the tibia exerts on the ankle joint? What is the magnitude of the force that the Achilles tendon exerts on the heel? So we're looking at two different forces. The force of the bone on the foot we want to know about, and the force of the tension of tendon on foot. So we got to sketch the Achilles tendon and tibia a little bit. We're defining it, defining just the foot as our system. The axis of rotation is where the leg bone meets the foot, basically the ankle. It says the foot's barely off the ground, so we're just going to pretend that there is no angle. We're going to neglect the angle between the foot and the ground and consider the foot horizontal. The gravitational force exerted by the foot on the earth, so the weight of the foot in this problem is pretty small compared to everything else, so we're going to ignore that too. I think I can go with that. So the only other things I wanted to mention were the torques, and I didn't put in the point of rotation on this one. It would be right there, or axis of rotation. So a force going up would cause a rotation like that on that particular one. This doesn't cause a torque because it is at the axis of rotation. This one would cause a rotation somewhat like that. We can sort of figure out what the force of the foot on the floor would be. It would be the body weight, essentially, because all your body weight would be on your toes. Yeah? We do know something about the force of the foot on the floor. It's going to be body weight for the most part. So mass of the body times gravity. Except for, this is 1 foot. You have 2 feet. So half your body weight should be on each foot. So we're going to say it's equal to those divided by 2.
Get a protractor. Or not.
The first way we're going to start to figure stuff out is using torques. So the sum of all the torques have to be equal to 0. Really, we've only got 2 torques here that we're concerned about. So the torque, or the tension of the tendon on the foot times the length of the tendon. Now in this example problem, they don't worry about the sine angle. Since everything's at 90s, all sine 90 is 1, we're not even including it or worrying about it at all. Because this is causing a positive torque, we're going to put a positive sign there. Force of the bone on foot, we're not going to worry about that because the distance from the point of rotation is 0, meaning that term is 0. So we've got the force of the floor on the foot. Times the length to the floor, or length along the floor from here to here. And we're saying that this is going to cause a negative torque, so we're going to make that a negative term. All that stuff has to be equal to 0. Something else that we can make note of is that we know that the force of the floor on the foot, we also know that the force of the floor on the foot is equal to the, we'll save this for later, mass of the body times gravity over 2. You must be on both feet, and we're only measuring 1 foot. So we're just going to sort of leave that there for now. The other thing that we know, and I'm going to use a different color so you know why I'm doing a second equation, is we know that, no, I don't want to do that. I want to do it in the same color. We want to know essentially about this, the tendon on the foot. If we were to solve for this, you'd have to get all this on the right, and you divide by length of the tendon. So without going through all the steps, the tension of the tendon on the foot is equal to mass of the body times G over 2 times the length of the floor over the length of the tendon. I didn't want to go through all the steps of algebra from here to there, but that's what we'd end up with. The other equations that we're going to want to use, or the things that are going to help us out, is that we know all the forces have to be equal to 0. So the forces in the y direction have to be equal to 0. As far as forces that we have the tension of the tendon on the foot again. We have the force of the bone on the foot. We have the force of the floor on the foot. And all those things are going to have to be equal to 0. As far as whether they're positive or negative, we have to look where the arrows are pointing. These two are pointing up. They can be positive. This one's pointing down. It can be negative. So force of bone on foot, we're going to call U negative. The other ones can be all positive. We also said that force of floor on foot was equivalent to mass of body times G over 2. That all should be in the parentheses, which is pretty nasty. And we're going to use this to figure out tendon on the foot. We're going to use this to figure out the other thing that we need to know, the bone on the foot. So if I were to solve for force of bone on the foot, personally, I would want to move it to the right side so that it is positive. And then the other terms would have to be on the left. Well, they already are. Tension of the tendon on the foot. And then I'm going to replace force of floor on foot with this. So plus mass of the body times gravity over 2. That's going to be our second equation that we're going to use. Between those two equations, we're going to take care of what we need to know. So, one thing that is provided to us later in the problem that we wouldn't be able to do anything with otherwise is that the length from that point to the floor is 5 times longer than that point to the tendon. That helps us out. Otherwise, I don't know how we would do this. So, nice little hint that we're given later on is that the length to the floor is equal to the 5 times the length to the tendon. What that means is this term, or I don't even know what you call it, this ratio is equivalent to 5 to 1. Floor is 5 times larger than the tendon. So we could say it's the mass of the body times G over 2 multiplied by 5. Yes. You can also say it would be equivalent to 5/2 of mass of body times G. Then we're given another little hint within it. If let's say we pick a mass for this person. If it is a 70 kilogram person, and we were to punch this in 70 times 9.8 times 5 divided by 2, they're saying that this is going to be about, and I think they take it times 10 for easier math, about 1,750 newtons is the tension of that tendon on the foot. That's a lot. So it's 5 halves your body weight. It is 2.5 times your body weight is what that tendon is pulling at the time, which is quite a bit. The other thing that we were wondering about was the force of the bone on the foot. So I might steal this equation. We have pretty much all the information we need now to do force of the bone on the foot. We figured out that the force or the tension of the tendon on the foot is 1750. So we can go ahead and put that in, 1750. Mass of the body, we said was 70 kilograms. G, they were using rough estimates here. They're saying about 10 newtons for every kilogram. Gravitational field force. Yeah. Over 2 would be equal to that force of the bone on their foot. Which ends up being around 2,100 newtons. Take-home message is that in this position, the tension of the tendon on your foot is about 2.5 times your body weight, and the force of the bone on your foot is about 3 times your body weight. So it's a lot.
Can we do